All right, and we are back for the second hour here on Monday, doing the second part of 27 carbohydrates. Keep in mind these things here, especially homework due, and then quiz 8 due tomorrow, but you'll get some time to help out with that. All right, where we left off was cyclizing the monosaccharide here, the most common one being glucose, the most important one. And how do we get to the alpha and the beta anomer forms in the cyclic pyranose form, which is the pyran cyclic form, hemiacetal? A lot of terms there. Keep those straight. I'm not defining each one on the board here, but it's on the outline for the chapter and, of course, in your book. But trying to go through structurally and show you how we arrive at this. The open form in aqueous solution in water is only about 1% at equilibrium. Okay, so we do have equilibrium arrows here. And we're drawing new conformations of this same thing. And we're showing what? Up, down, down there. That's these guys when you tip it on the side. Okay, you should go through that physically with models to make sure you can see that. Or assign RNS to each stereocenter there. And this is D-glucose. This last stereocenter is on the right. Indeed, it is dextrorotatory. Sometimes glucose or blood sugar is called dextrose in the clinic, actually. Those ringer solutions that you can be given intravenously if you're dehydrated or whatever, are 5% glucose solutions. They call them dextrose solutions, but it's glucose, aqueous dilute glucose. So how do we get at this? So here's our conformation, and how do we get to the beta anomer? And this beta anomer is going to look like this, right? It's going to have that in the up equatorial position. And yeah, go ahead and draw in all the other stereocenters, what, down, up, down. So there's the whole thing there, all equatorial. And you see down, up, down, and I'm just abbreviating them as those lines there, but those are alcohols, okay? And so how does the cyclization occur? Well, it's happening in water, so you can actually draw a water molecule up here and see that you just exchange hydroxyls here for this. You don't need to protonate it. We're not in strong acid, we're in neutral water here. So how is this going to occur? Well, this is the important direction here, the lone pair attacking here. And then what? This pair of electrons out of the pi bond can grab a proton there. And then what? A lone pair on a water molecule can grab that proton and then leave those electrons on the pyran oxygen here. And that motion here, you see, just reforms a water molecule there and provides a pathway to exchange the aldehyde version with the pyranose version, okay, the pyran. And if the aldehyde is up like that relative to this, that's called the beta anomer, okay? Up relative to the last stereocenter. And that's how these designations are. The beta means up relative to the last stereocenter right there. So it's on the same side of the flat Hayworth projection. The last one, the C6 position, and the new OH group are both up there. So that's beta. And how do we do alpha here? Well, same thing. Let's have a water molecule. And now we have the aldehyde oriented downward, you see. The key thing is that motion of electrons out of the lone pair on the C5 position. Alcohol coming over. And as it does that, it can grab a proton off there, right? And that can put those electrons back on this oxygen. That oxygen can grab that hydrogen off there, and we get what the alpha thing down. You see your hydrogen right here is in the up position. Your alcohol comes from the aldehyde being downward oriented there, and you regenerate what? A water molecule, of course. Okay, so that's the same thing, right? And there's our C6 position, down, up, down there. That's the glucose position. Now, you can take alpha and beta, and which is more stable, and this is going to tie into this mutarotation idea here. So stay tuned for what we need to look at here. We're going to take the pure alpha and beta forms, and if you purify this, recrystallize, And this is done by cooling down a solution of this in ethanol. And if you cool down a solution to about 0 or 5 degrees C here of the mixture, okay, alpha and beta, or this whole thing, okay, take this whole thing that's all in equilibrium here, going back and forth here. And you can go from the alpha back to the beta, right, if you equilibrate it all the way around there. And you can just reverse this, right? You can use the water to deprotonate here and flow the electrons back and grab the proton there and go back to this, right? That's what the equilibrium means. But if you recrystallize here and get the solid form to come out from ethanol, you actually get the alpha form pure, okay? That's a solid. And if you recrystallize this whole mixture, and that's what we mean here, this whole mixture here, if you recrystallize this mixture from cold water with a little bit of ethanol in it, you actually get out the pure beta form, okay? And again, as a solid, we're talking about recrystallizing that. So then you can take the alpha that's pure and do the optical rotation of that, and it turns out to be plus 112.2, okay? So very dextrorotatory, that's the little d here. You know it's the big D sugar because the last stereocenter is to the right. But yeah, plus 112 for the optical rotation in degrees there in the polarimeter. And that's the pure solid material, okay? So we know it's the pure, and actually you can get a crystal X-ray structure of it and know that it's, you know, the absolute stereochemistry. You can take this solid beta material that's pure here and also do the optical rotation of that, and what is that? Well, that's plus 18.7, okay, degrees. Okay, so they're different, right? They're diastereomers of each other, the alpha and the beta. Why are they diastereomers? Because there's one stereocenter that's different. All the other 4 stereocenters are all the same, right? But the relationship between alpha and beta anomers here are diastereomeric. Wow, a lot of D's floating around. This means the relationship stereochemically between the two. The D here means dextrorotatory. And this one's dextrorotatory also, but that's the beta anomer in the solid form here, okay? Now, if you take the mixture, okay, in the mixture of, you know, just glucose, D-glucose, and have it in water, okay, and do the polarimetry of that, of the mixture, you get plus 52.7 degrees in the polarimeter. Well, what's up with that? The alpha is 112, the beta is 180. So what's this plus 52.7? Is that a new molecule? No, that's again the mixture of what? Alpha and beta. Which one's dominant? I think we can tell which one's closer to 57 here. Yeah, it's beta. So actually at equilibrium, how much beta do we really have? And mathematically, you can go through these numbers and figure it out. Beta form is 64% at equilibrium, and the alpha form of glucose is what, 36%, okay? That's because mainly you're seeing the beta form, that's the major one, and the alpha we'd say is minor. Well, why is that? We need to look at the 2 forms here. Okay, if beta's major, you can say, well, it's equatorial, right? And so by sterics, you could say, yeah, that's a little bit better. That's a less sterically encumbered position. When you put the group here, what, axial in the alpha form, look, that's close to these other groups that are also axial down here. Their hydrogens are relatively small at that point. But the axial is actually favored electronically. And the electronic factor is the fact that the sigma star right here of the carbon-oxygen bond is right there coplanar with the lone pair electrons, okay? And that lone pair overlap actually is a stabilizing effect, even though it's a counter-steric argument. So you could say sterics would favor that, and also this is a better hydrogen bonder to water, So you're in equilibrium after all. Why is this a better hydrogen bond or beta? Because it's more exposed to the solvent. This one's tucked under a little bit, being axial, so it's not solvated as well. But it has this electronic effect of the lone pair into the sigma star. See, the sigma star is right here in the equatorial one, and that's remote from the two lone pairs here on the oxygen. But if it's in the axial position, you see the lone pair is right there coplanar with that. Okay, it's called the anomeric effect. And so that's why we have a lot of alpha at equilibrium. Pure alpha is what? 112.2. Pure beta is 18.7. Now, don't memorize those numbers. I don't care about that. But the actual rotation that you see, if you let it go with time here, and it takes some time, you can take the mixture and get the 52.7, or you can take pure alpha, or what? Pure beta, and let it go with time there. It takes a couple hours, and you can watch in the polarimeter. You can watch the initial pure alpha rotation of the polarimeter, 112. You can watch it slowly go down to 52.7. Why? It slowly goes to that equilibrium mixture, 64.36. You can take pure beta, which starts out as plus 18, and let it equilibrate over time, and it goes up to 52.7. Okay, what do we call this effect? This changing the rotation, change in the optical rotation in degrees there, right? We call that change mutarotation. Rotation, we're referring to the polarimeter rotation, and mutation meaning change. That change in the rotation is almost always seen with hemiacetals, okay? And of course, all the monosaccharides are hemiacetals. We'll see the disaccharides, polysaccharides, some of them are mutarotating, some are not. So glucose is definitely a mutarotating sugar, okay? Because it's changing its rotation in the pure alpha, pure beta form to this equilibrium value in the polarimeter. So that's what mutarotation means, that change in that. All right, let's look at the other effect here, which is going to be, oh, let me get rid of that. So we got the cyclic form, and we can always go back to the open form. Okay, so it doesn't mean the open form's not there, it's only 1%. And then we can take this with silver oxide, and it's usually a solution of ammonia and hydroxide here. And we're gonna form the Aldonic Acid. Okay, so this is Gluconic Acid, it's called. And what do we mean? Why is this an acid? Well, carboxylic acid right here. And so that definitely got oxidized. And so something must get reduced. And what is it? Well, silver here goes from the silver +1 oxidation state. Remember, oxide is -2 anion. So this is silver oxide. You'll see the solution here in a second. We're going to do this reaction with the ammonia and the base. And it goes to the gluconic acid. And the byproduct is the silver metal, silver in the reduced form. This is called the Tollens test, or the Tollens reaction. And what are we testing for? We're testing for the presence of a hemiacetal, okay? Because hemiacetals are always in equilibrium with the free aldehyde. And it's that aldehyde that's selectively getting oxidized by the Tollens reagent. I could show you the mechanism of that. I'm not going to show you. Well, nah, let's see. I guess we could show you a little bit about it. So it's actually this hydrate form, which has the silver on it. So the silver in the water converts it to that, and then the base actually pulls the proton off at that aldehyde position, and then you push the electrons into silver. Oh, there, I guess I showed you the mechanism of the Tollens reaction. And what do we say here? We say it's the silver got reduced. The aldehyde got oxidized, but the test is for whether or not it can reduce silver. So we say, is this a reducing sugar or not? Well, yeah, you'll see the positive test here. You'll see the silver mirror coming out. So what we'll say is that glucose, or any hemiacetal sugar for that matter, will give a positive Tollens test. It will show a reduction of the actual reagent, the silver 1 going to silver 0 here, because of that free aldehyde that can form that intermediate there. Now, if it's an acetal, okay, a full acetal, it will actually be negative. It'll be a non-reducing sugar, okay? So when we look at the disaccharides and the others here coming up, we'll be able to test whether or not there's a hemiacetal in the structure or not, okay? So that's what that means. So it also means, you could potentially convert it into something else. So it says something about the reactivity and the structure of it. But yeah, the two things, mutarotating sugar, if it's hemiacetal, and then reducing sugar, mutarotation and reducing. Let's see if we're ready to do this demo here. We're going to show you the Tollens test. And yeah, that's probably hot enough. So we're heating up just a water solution with our flask right now, and I'm going to turn that off because I think it's hot enough. And yeah, hopefully I won't burn myself or anything. It is very hot, so I've got the mitt there. And actually that step is just to heat up the flask. And we're going to put in our Tollens solution, which is the silver ammonia hydroxide. There we go. And we're going to put in, let's see how hot that still is. Okay, maybe we can see a little better over here. We're going to put in the sugar now. This is just a glucose solution. Dextrose is on the bottle. Remember I said that's a common name for glucose because it is dextrorotatory. Let's get that in there. So what you notice right away is it turns black. That's the silver oxide coming out. If we keep shaking it, let's see. What do you notice the flask it's turning into? It's kind of cool, I think, isn't it? It's turning into a mirror, right? Where's that mirror coming from? Well, the mirror is the reduced silver plating out on the inside surface of the glass, okay? It doesn't have an affinity for water anymore. It's in the reduced state. So it's plating out, forming a solid, very thin layer on the interior of the glass flask. And wow, I can see myself there. I'm kind of distorted. I kind of look a little better actually in the flask. No, okay. This is how mirrors were actually made in the old days. If you've ever been to the Hall of Mirrors in Versailles and in Paris, it's a whole wall covered with mirrors, and that was very difficult to make mirrors of that side back then. And what you also notice if you're at Versailles, around some of the edges, it's kind of turning black, some of the old mirrors, and that's because the silver is getting reoxidized back to the silver 1 or silver 2, which is a black color. But yeah, so that's how mirrors are typically made, and you just see the byproduct there. The silver got reduced. So what do we say about the sugar? We say the sugar is a reducing sugar, not referring to itself, because the sugar actually got oxidized to the aldonic acid. The silver is what got reduced, okay? But that's how we talk about the Tollens test. Is it a reducing sugar? Does it give a positive Tollens test? Or if it's an acetal, it's not in equilibrium, you see, with the aldehyde, okay? And remember we said ethyl acetals, and you'll see that later a little better, are stable. They're not forming the aldehyde, so they won't give a positive Tollens test. So this is a way to tell whether you've got one structure or another. Anyway, so people sometimes ask me if they can have the flask or how valuable is the silver. Well, it's actually a tiny amount of silver. It's a dilute solution. And the thickness here is just a few atoms thick of the silver. And they actually treat it with nitric acid in the demo lab and get that silver back off, and they can put it back in solution. So you can do a similar thing with copper. It's called the Benedict Solution. And that's also mentioned in your book. I kind of showed that instead of silver +1 reagent, you have copper oxide, which is copper +2. And it does a similar thing. It goes to reduced form of copper, and it actually gives the reddish silvery color like a penny, right? Like copper more reddish metallic sheen to it, which is kind of cool there. Anyway, that's a neat thing. Connection between sugars and metals that way. Kind of fun. All right, what else do we need to get to? So let's look at a couple of acetal forming reactions now. So we're going to take our sugar, glucose here, and let's take the cyclic form and react it with some different reagents. So I've already shown you some reactions, but let's take this mixture, and it can be a mixture of alpha and beta. Let's see, which one should I show? Oh, let's show the major one, right? That's beta. How do you know it's beta? It's up right there, okay? And if you keep the same orientation, remember this edge is coming out at you there. So this is up relative to that stereocenter, okay? So that's indeed beta. But, you know, if you put it in solution, it'll start to give a mixture, start to give some alpha, okay? So you can start out with either one here in this case. And we're going to treat with methanol as our solvent, and we're going to add a little bit of acid, catalytic sulfuric acid. And what are we going to get here? We're going to get the methyl acetal. The alcohols are going to stay the same there. And we're going to get the methyl ether right here. Notice that's now an acetal. Okay, I'm showing the beta one. You actually get plus some of the alpha one. Okay, up and down there. And if you take the optical rotation of this, let's get pure beta. If you recrystallize it, you can get the pure beta methyl glycoside, this is called now. We have a full acetal at that position. We'll go through the mechanism in a second, and we'll talk about why you don't get any of the methyl ethers here. You just get the methyl ether right here at the 1 position. Okay, why is that? Be thinking about that. Well, let's think about first taking the optical rotation of the pure beta form here, and what do you get? You get plus 36 degrees, okay? And you can actually put that in solution in water or base. Will it mutarotate or not? No, this 36 degrees will stay there. We say it's not mutarotating. Why? Well, it's now a full acetal. And if it starts out in the pure beta form, it'll stay that way. Why? Because this is a diether now. In order to get it to change, we have to put it back in acidic water and hydrolyze it back to the hemiacetal first. So once we form these acetals, or these glycosides, and we don't have a free aldehyde there, there's no equilibrium now with the aldehyde form, okay? Unless we hydrolyze it and go back. And you can see the optic rotation, because it's the diether acetal, no mutarotation. And that's a way to tell whether you've got the hemiacetal or the full acetal form of something. The optic rotation typically will not change. All right, what was the mechanism here? Well, we protonate right there. We could have protonated any of these alcohols, right? Why are we protonating there selectively? Well, when we do that, we get this. We get the carbocation there, right? I'm not drawing the rest of the alcohols off there. But if we protonate and then pull off water there, we get a secondary carbocation, which we would have gotten here or here or here. This would have been a primary carbocation, would have been unfavorable there. But why is this secondary carbocation better than these other 3? Right, it's due to the resonance effect. So you've got these lone pairs here that can resonate in there, right? So double-headed arrow now, and you want to flatten out that position in the molecule. You still got all the other alcohols on there, okay? But this carbocation now can undergo the attack by what? The nucleophile, the weak nucleophile, which is the solvent. Let's go ahead and have it come in there. And it can come in from the top or the bottom, right? So let's see, if we come in from the top there, okay, we're going to get this. And we'll have that initially protonated, right? And so we'll have to then take that off right there. And we can use methanol, more methanol, to deprotonate there. And then that goes to what? That goes to the beta hemiacetal form. Now, like I said, you're forming a mixture of both the alpha and the beta acetals in this case. From the top here would be the beta, right? You could also go from the bottom, right? And that would give you this. So add in your other alcohols if you want to around there. This is the, came in from the bottom, so this hydrogen right here. And draw those in. There's still a hydrogen right there on the side. If we came in from the top, this hydrogen was pushed down, right? If it came in from the bottom, this hydrogen's pushed up. And you see loss of the proton there will give us the alpha form of the methyl glycoside. But we can tell by the mutation. We can purify the alpha, recrystallize it out of there, and we can do the same trick there. If we put it back in pure water or basic water, it will stay its rotation. I don't have its rotation, but okay, yeah. All right, another reaction here with glucose. Let's get some more room here. Let's see here. Let's take glucose again and treat it with acetic anhydride and pyridine excess. Okay, so when we did the methyl glycoside, we had excess methanol. We were in the solvent methanol. Now what are we going to get here? If we put this in there, we're going to get acetates on every spot. And that's different, right? Because we've got acetic anhydride. That anhydride's very reactive with alcohols. That's a reaction we learned in chapter, what, 21, the derivatives of carboxylic acid chapter. We're also going to get the beta form here. Or I'm sorry, I'm showing alpha. Which one do I want to show? Oh, let's do beta. Okay. You actually get a mixture, beta plus alpha, okay, with all the acetates at that spot, okay? Now let's take this and put it in water with dilute HCl. What are we going to get here? Well, we could hydrolyze back off all of these and go to glucose, but if we do dilute HCl with a limited amount of time, look, we can go back to the hemiacetal form here. This is going to be more labile there. We can protonate this acetate and get the more stable carbocation, right? These don't have the resonance stabilization. They can come off at this point, right? But this one will come back off and it can leave behind all the acetates, okay? Which is kind of cool there. So you can differentially do things there. And then this one will be mutarotating. If you purify out the alpha or the beta, put it back in solution, you'll see the optic rotation change. And it is a reducing sugar. Okay, why? Because it's now the hemiacetal. Whereas this one is an acetal. Okay, let's take this one that we had the methyl on the glucose. Okay, and let's treat that with the same thing, with the acetic anhydride. And we'll get our methyl ether still there and our acetates still on there. And you see that's another way to get different ones on there. And you know, this is stable to base, so there'll be no reaction here. But these we could take off with hydroxide, okay, and have different type of products showing up there. But the methyl ether there is good there. And then you can also take the same thing with water here, well, dilute HCl. And just like before, this is the labile position under what? Acidic conditions. And you can get that to come off. And the acetates will still be on there. So what do we have? The acetate there and there. A lot of chalk today, sorry. And now that's the hemiacetal. That'll be mutarotating or reducing. Well, it's the same thing. Should have just drawn that there. Yeah, so that gives us a difference for that. But yeah, you can see the different reactions there. One more here. Let's take glucose itself and treat with methyl iodide and silver oxide. Okay, so that's the same Tollens reagent here, but it's not under basic conditions with the ammonia, so it's not doing the oxidation thing. It's just functioning as a base to activate all the alcohols to be nucleophiles, and then excess of the methyl iodide will give us this. So we'll have all methyl ethers on the whole molecule, and mainly be beta, but you'll get some alpha there. And then what? You can take that and you can treat that, you see, with water and acid. And what's going to happen here? Well, here's your acetal, okay, carbon, and these are now not metarotating, not reducing, right? Because they are acetals, okay, just like these others we looked at. But now we have methyl ethers at every spot. Which methyl ether is going to come off under the hydrolysis conditions? Yeah, it's just going to be this one. These are just simple ethers. Those are stable. But the acetal ethers are going to be able to come off. So you can protonate there, lose that, carbocation, and then attack with water. I'll let you do the rest of the mechanism. But what do you get there? You get the hemiacetal methyl ether version. Okay, so those are all methyl ethers still, and the hemiacetal goes back to the alcohol there. Okay, why? Because you're in the presence of water and acid. You have the ability to protonate that, turn that into a leaving group. Now you gotta be able to protonate that to get it to come. And if it's an acetal, there's no proton on there to interact with water and go back to the hemiacetal. So if there's an R group there, another group that's not hydrogen, these are acetals, and they're stable to neutral and base, but they will come off with the acid in that case. Okay, so that's a lot of reactions there. Yeah, Tollens test, we've already done that. I'd like to do a little bit now on fructose. Do the cyclic form of fructose, and that'll probably be it for today. We'll do some other glycosides, of course, and the disaccharides and the polysaccharides next time. But let's take now glucose and treat it with something else. Actually, let me get another board down here. Let's take glucose, and we're going to isomerize it. And you've probably heard of fructose, and probably a lot of you have heard of the term high fructose corn syrup, right? So let's see, let's start with glucose. Right, left, right, right, right. Okay, that's glucose. D, dextrorotatory, whatever, glucose. And let's isomerize this now with isomerase. Okay, so what do we mean by that? Well, ACE implies it's what? An enzyme, okay? These are found in nature. You're able to convert glucose into fructose. And what does fructose look like? Well, it's very similar to glucose, except at the 2 position, it's a ketone, okay? So instead of having an alcohol here, but then all the other stereocenters are the same, left, right, right. So look at these last 4 carbons. To the left, there's that alcohol. To the right, to the right. So it is a D sugar. This is D fructose, okay? It's no longer an aldose. What do we call it? It's in the general family of ketoses, right? Okay, which means it's a ketone at that position. You might think, well, how do you go from an aldehyde to a ketone? Notice it's the same molecular formula. It's still C6H12O6, but these are what? Constitutional isomers of each other. These are not stereoisomers. How do we constitutionally switch the carbonyl from the 1 position to the 2 position? How does this isomerase work? Well, we can imagine in this enzyme, there's a specific base. It turns out it's a histidine, imidazole, and it will take off this proton and what? Dump those electrons in there, and then this can grab on a protonated form here. I forget which one it is. I'd have to look at the enzyme, but this is the enzyme here we're talking about. Isomerase, it's called. What's the intermediate look like if we do this? Well, we'll have a hydroxyl there, and look, if we dump those electrons down here, we're going to have this, right? And then all the others are the same. Left, right, right. What do we call that intermediate? It has a name. It's an alkene alcohol. It's, yeah, the enol form, okay? It's the tautomer, you'd say, right? The tautomeric relationship. These are isomers that are related to each other just by the movement of a hydrogen atom, okay? Well, let's see, what else can this enzyme do? There's a base that can what? Take that proton off, deliver those electrons here, and then protonate up here, okay? So within the same enzyme, you know, we've got a general specific base here, take the proton off, liberate the electrons to go down and form what, the carbonyl right there now. And then protonate up here, which will give us that hydrogen transferred from up there. So this hydrogen just gets transferred from the 2 position over to the 1 position, and the ketone is formed there, okay? So that's called fructose. It's very prevalent in fruits. It's quite a bit sweeter taste-wise than glucose. Fructose, or fru, is made industrially using this isomerase enzyme to take glucose that comes out of corn or sugar beets or whatever and turn it into a syrup that has a higher percentage of fructose. Now, why would they want to do that? Well, again, it tastes sweeter. And if you're getting more of the sweet taste with what? Less of the carbs, that's a beneficial health thing, right? So high fructose corn syrup is actually an attempt to make a food product derived from corn or sugar beets that has a lower caloric content in the diet. Okay, you don't need to add as much to foods. It has a sweeter taste with lower amounts of carbs. Now, I'll mention later on in metabolism, fructose is actually metabolized a little bit different than glucose. If you don't need the energy, too much fructose is converted more quickly into fats, okay? So that's probably the bad thing about high fructose corn syrup that some people complain about. But here we are to fructose. We need to look at the forms of it. This is just the ring open form, the ketone form. And the ketone here exists mainly as a cyclic form. So let's see here. Let's take fructose and put it on its side. And conformationally, we're going to have to, see how this thing might cyclize. All the stereocenters are still the same there. We've got, up, down, down now. That was the same as left, right, right. And they are related stereochemically. These last 3 stereocenters are the same in fructose compared to glucose. And, the enzyme just messes with the C1, C2 position, just exchanging that to get the different isomer form. So how do we go from this to the cyclic form? Well, we're going to have this at the 5 position functions as our nucleophile onto the carbonyl. Now, we need to look at a little bit different orientation here. So at that point, we've got this, which is coming around and cyclizing on there. And we've got, what here? We've got the positions here that are going to be a little bit different in fructose, right? Because we've got this position here, which is the 1 position, and here's our 2 position. So we can have that 1 position right here. Here was our ketone, which means this is now what? A hemiacetal. Okay, so cyclizing on to that 2 position there gives us the same ether alcohol, which is what a hemiacetal is, right? And then what are these other groups? Well, this is up right here. Okay, and this is down right here in fructose. And then we have the same thing over here with the 6th position being a primary alcohol And here's our 5 position, which is also up. So it's still that D sugar, okay? But the front edge is coming out at us here. And again, I kind of skipped some steps there and the participation of water. We could go through that. What am I drawing here? Am I drawing the alpha or the beta form? Let's see. We've got the alcohol down here across from the 6th position carbon. So what are we going to call that? Yeah, that's the alpha. Is there also a beta form of fructose? Yeah, let's get that here. So if we cyclize the other way with the ketone sticking up, we would have gotten the alcohol up. And you see that 1 position, the carbon right there. But all the other stereocenters are the same. Okay, so let's see. This alcohol you see is now up relative to this 6th position. Again, that's the 2 carbon where the ketone was. Now it's a hemiacetal. And because it's up there, what do we call this? This is now the beta form. Okay. Beta fructofuranose. Let me give you the whole name here. Beta D fructofuranose. Before we had pyranoses, right? We had glucopyranose for glucose, and pyranose referred to the 6th ring heterocycle. But now we have this term, furanose, actually as part of the suffix fructo, referring to the sugar it came from. What's furan referring to? Right, furan refers to the 5-membered heterocycle, okay? So that's a furan. So it kind of refers to the heterocycle that we're looking at there. But yeah, this would be the beta form. Why? Because that's up relative to that. The alpha form with that down. Yeah, I think that's all we really need to say there. And it is the D sugar. Why? Because that stereocenter right here is R. It's in the up position on there. And that keeps track of that, I think. All right. I think we're okay stopping at this point. We'll say a lot more coming up with the disaccharides, and we'll review, of course, this concept of mutarotation and the optical rotations being changing there. If there's a free hemiacetal in a sugar, it will be mutarotating and it will be a reducing sugar. But if it's tied up as a full acetal, we'll look at the properties changing there. And we'll get into the disaccharides, the ones you know and love, maltose, cellobiose. Well, you've probably heard of sucrose more, table sugar. We'll look at that and the different aspects of the structure of that. So stay tuned. We've got a couple more class times on chapter 27 here, and we'll see you next time. Very good.